You're listening to recording 1C in our series on reciprocal functions for Unit 7, Chapter 7 of Mathematics 2200. Now we're going to do the reciprocals of quadratic functions. In this example, we're asked to graph the reciprocal function for y equals x squared plus 4x minus 5. We find its y-intercept simply by putting in 0 for the x, a y-intercept at 0, negative 5. Next, we do the x-intercept. So putting in 0 for y, as we've done before, we have 0 equals x squared plus 4x minus 5, and we can solve that quadratic equation by factoring. We get negative 5 and 1. So we have x-intercepts at negative 5 and 1. Now pausing with that much for a moment, the reciprocal function is y equals 1 over x squared plus 4x minus 5. But to see the non-permissible values, we need to factor the denominator. So that's really 1 over x plus 5x minus 1. So the non-permissible values are the same as the x-intercepts for the original parabola. X equals negative 5. X equals 1. So I draw in my vertical asymptotes at those two locations. While I'm at it, the y-intercept of the parabola is 0, negative 5. So for our reciprocal graph, that will end up at 0 and negative 1/5, right around there somewhere. Now another important point for a parabola is its vertex. Negative b over 2a is the easiest way to find the vertex here. Substituting that into our function to get the y-coordinate of the vertex. So our vertex is at negative 2, negative 9. Let's plot that. Negative 2, negative 9 right there. So the vertex of our reciprocal graph will be at negative 2 and negative 1/9, which is right here. There we go, very close to the x-axis in this case. Next, we find the invariant points. When y equals 1, first of all, we set x squared plus 4x minus 5 equal to 1. And when y equals negative 1, we set the function, the expression x squared plus 4x minus 5 equal to negative 1. They're both quadratic equations now, so I have to make them equal to 0 to solve them. Minus 5 minus 1 would bring that 1 across, it'll be minus 6. And over here, it'll become a plus 1, so I'll have x squared plus 4x minus 4 equals 0. Now, unfortunately, neither one of those will factor, at least not easily. So we will have to use the quadratic formula. So I've got negative 4 plus or minus here, the square root of 4 squared, minus 4 times 1 times negative 6, all over 2 times 1. That gives us negative 4 plus or minus root 40 over 2. Using our skills with radicals from Chapter 5, we've got x equals negative 4 plus or minus 2 root 10, all over 2. Expressing that root 40 is a mixed radical. I'm out of space here, so I'm going to have to move up here. X equals, divide the 2 into both of these coefficients, so I've got x equals negative 2 plus or minus root 10. So x equals negative 2 plus root 10. That works out to approximately 1.16. And x equals negative 2 minus root 10. That works out to approximately negative 5.16. So we've got invariant points at approximately 1.16, and when y is 1, and negative 5.16 and 1. We've got another set of invariant points from this equation, so I'll just work it out and put the answer there. So here are my invariant points when y is equal to negative 1. So we put those points back on our graph I'll also color them brown so we know that they go on our reciprocal graph as well as our parabola. So there are the 4 of them. So I've sketched in my parabola, y equals x squared plus 4x minus 5. That'll be a bit of a guide here. Now from here, because it's only a sketch, I can use that parabola as my guide by doing an analysis. I've got an invariant point right here, and back here before the invariant point, the parabola has large positive y values. So the reciprocal of large positive will be small positive. So we can just do a reasonable guesstimate, I call it, of what that graph looks like. The smaller the positive, the larger the reciprocal, of course. So in between the invariant point and the asymptote, we've got really small positive, or we're getting to have really small positive y values. So the reciprocals will be large positive after the invariant point. So we're going to get really close to that asymptote, but we're not able to cross it. Pretty difficult to draw it as close as we have it here. But you got to do your best. Don't cross that asymptote. Likewise, in between the asymptotes, we got a couple of points here that we can go by, invariant points here and here as well. So I can connect those. Something like that. And then between the asymptote and this invariant point, I got small negatives. So for the reciprocal graphs, I'm going to have larger negatives, getting close to the asymptote. And I've completed the graph using a similar analysis over here, or this piece of the graph. Now I've got another piece right here. Small positive becomes large positive. And then after the invariant point, the large positive will become small positive when I take the reciprocals. So my graph looks something like this. For a little more accuracy, you can take some points close on either side of each vertical asymptote. I've taken negative 5.5 and negative 4.5, plug them into the parabola function, take the reciprocal of the point, and then I will have points for my reciprocal graph. Don't forget to take a couple of points here for the end behavior within the bounds of your scale. In summary, here are the steps for graphing the reciprocal of a quadratic function. Find the x-intercepts to get your vertical asymptotes for the reciprocal function. Find your y-intercept of the quadratic. That'll give you the y-intercept when you take the reciprocal for the reciprocal function. Find the invariant points and use a few points for accuracy. That's a little bit optional, but make sure you got some reasonable accuracy to your graph.